Installing K-rated transformers with a higher K rating than required can indeed create problems. Higher K-rated transformers have more impedance, which can lead to increased harmonic distortion in the output voltage. This can be problematic for sensitive electronic equipment, which can be damaged or malfunction due to harmonics. Transformers with higher K ratings have higher losses, which can reduce the overall efficiency of the power system. Transformers with higher K ratings are typically more expensive than those with lower ratings. Installing a higher K-rated transformer than required may result in overloading the transformer under certain operating conditions. Overloading can lead to overheating, insulation breakdown, and transformer failure. Transformers with high K ratings may have poorer voltage regulation than those with lower ratings. This can result in voltage fluctuations and instability in the power system. Higher K-rated transformers are typically larger and heavier than those with lower ratings, which can make installation and maintenance more difficult. Higher K-rated transformers are only recommended for use in specific applications where they are required to handle high levels of harmonic distortion or transient loads. In most cases, it is better to use the lowest K-rated transformer that meets the specific requirements of the application. It's important to select the correct K rating for the specific application. Installing a transformer with a higher K rating than required can create more problems than it solves. Firstly, let's delve into the concept of K-rated transformers and harmonic distortion. Harmonics are essentially distortions of the ideal sinusoidal waveform of alternating current or AC power. These distortions are caused by nonlinear loads, which draw current in a non-sinusoidal manner. Examples of such loads include computers, variable frequency drives or VFD, electronic ballasts, and other electronic devices. These nonlinear loads generate harmonic currents that flow back into the power system. These harmonic currents can cause a variety of problems, including overheating of transformers, increased losses in the power system, and malfunction of sensitive electronic equipment. K-rated transformers are designed to mitigate the effects of harmonic currents. The K rating indicates the transformer's ability to withstand the heating effects of harmonic currents. A transformer with a higher K rating can handle higher levels of harmonic distortion without overheating. However, installing a K-rated transformer with a higher K rating than required can lead to increased harmonic distortion. This is because higher K-rated transformers have more impedance. Impedance is the opposition to the flow of alternating current. A higher impedance can cause harmonic currents to be amplified, leading to increased harmonic distortion in the output voltage. This can be problematic for sensitive electronic equipment, which can be damaged or malfunction due to harmonics. Secondly, consider the issue of reduced efficiency. Transformers are not perfectly efficient devices. Some energy is lost in the form of heat due to various factors, including core losses and winding losses. Core losses are caused by the alternating magnetic field in the transformer core, while winding losses are caused by the resistance of the transformer windings. Transformers with high K ratings typically have higher losses than those with lower ratings. This is because they are designed to handle higher levels of harmonic distortion, which requires a larger core and heavier windings. The increased losses in higher K-rated transformers can reduce the overall efficiency of the power system. This means that more energy is wasted in the form of heat, which can increase operating costs. Thirdly, there's the aspect of increased cost. Transformers with high K ratings are typically more expensive than those with lower ratings. This is because they require more materials and more complex manufacturing processes. Installing a K-rated transformer with a higher K rating than required can therefore result in unnecessary expense. It is important to select the lowest K-rated transformer that meets the specific requirements of the application to minimize costs. Fourthly, examine the potential for overloading. While it may seem counterintuitive, installing a higher K-rated transformer than required may result in overloading the transformer under certain operating conditions. This is because the transformer's impedance can affect the current flow in the system. If the transformer is oversized, it may not be able to handle the inrush current that occurs when loads are switched on. This inrush current can cause the transformer to overheat and potentially fail. Overloading can lead to overheating, insulation breakdown, and transformer failure. This can result in costly repairs and downtime. Fifthly, let's think about poor voltage regulation. Voltage regulation is a measure of how well a transformer maintains a constant output voltage under varying load conditions. Transformers with higher K ratings may have poorer voltage regulation than those with lower ratings. This is because the increased impedance of higher K-rated transformers can cause voltage drops under heavy load conditions. Poor voltage regulation can result in voltage fluctuations and instability in the power system. This can cause sensitive electronic equipment to malfunction or be damaged. Sixthly, note the increased size and weight. High K-rated transformers are typically larger and heavier than those with lower ratings. This is because they require a larger core and heavier windings to handle the increased harmonic distortion. The increased size and weight of higher K-rated transformers can make installation and maintenance more difficult. This can also increase the cost of installation. Now, when is it appropriate to use higher K-rated transformers? Higher K-rated transformers are only recommended for use in specific applications where they are required to handle high levels of harmonic distortion or transient loads. These applications typically involve a high concentration of nonlinear loads, such as data centers, hospitals, and industrial facilities. In these applications, the harmonic currents generated by the nonlinear loads can cause significant overheating and damage to transformers. Higher K-rated transformers are designed to withstand these harmonic currents and provide reliable power to the loads. In most cases, it is better to use the lowest K-rated transformer that meets the specific requirements of the application. This will minimize costs, improve efficiency, and reduce the risk of overloading. To select the appropriate K rating for a transformer, it is necessary to perform a harmonic analysis of the load. This analysis will determine the level of harmonic distortion present in the system. The transformer should then be selected with a K rating that is sufficient to handle the calculated harmonic distortion. It is also important to consider the transformer's loading and operating conditions. The transformer should be sized to handle the maximum load that it is expected to serve. The operating conditions, such as ambient temperature and altitude, should also be taken into account. By carefully considering these factors, it is possible to select the correct K rating for the specific application and avoid the problems associated with oversized transformers. In conclusion, while K-rated transformers can be useful for reducing transformer heating, it is important to select the correct K rating for the specific application. Installing a transformer with a higher K rating than required can create more problems than it solves. These problems include increased harmonic distortion, reduced efficiency, increased cost, overloading, poor voltage regulation, and increased size and weight. It is therefore essential to perform a harmonic analysis of the load and select the lowest K-rated transformer that meets the specific requirements of the application. This will ensure optimal performance and reliability of the power system. When dealing with non-sinusoidal currents, which are common with modern electronic loads, traditional transformers can experience overheating due to eddy current losses and hysteresis losses. These losses are exacerbated by the higher frequencies present in the harmonic currents. K-rated transformers are specifically designed to handle these non-sinusoidal currents without excessive heating. They achieve this through several design modifications, including using a larger core, employing higher quality core steel, and utilizing enhanced winding configurations to reduce eddy current losses. The K factor itself is a weighting factor that represents the effect of harmonic currents on transformer heating. It's calculated based on the magnitude and frequency of the individual harmonic components. A K factor of 1 indicates a linear load with no harmonic content, while higher K factors represent increasing levels of harmonic distortion. Common K ratings include K-4, K-9, K-13, K-20, and K-30. Selecting the appropriate K rating involves analyzing the harmonic content of the load and choosing a transformer with a K rating that meets or exceeds a calculated K factor. As previously mentioned, oversizing the K rating can lead to several drawbacks. Increased impedance, one of the primary concerns, affects both voltage regulation and fault current levels. Higher impedance results in a larger voltage drop under load, potentially causing voltage sags that can disrupt sensitive equipment. Additionally, higher impedance limits the available fault current, which can impact the performance of overcurrent protection devices, such as circuit breakers and fuses. These devices rely on sufficient fault current to quickly trap and clear faults, protecting equipment and personnel. If the fault current is too low, the protective devices may not operate as intended, increasing the risk of damage or injury. Reduced efficiency is another consequence of oversizing. K-rated transformers are designed with specific core and winding configurations to minimize losses at the design K-factor. When operating at lower harmonic levels than the design K-factor, the transformer may not be operating at its optimal efficiency point, leading to increased core and winding losses. These losses translate into higher energy consumption and increased operating costs. The increased cost of higher K-rated transformers is also a significant consideration. The additional materials and manufacturing processes required to achieve higher K ratings contribute to a higher purchase price. Unless the application truly requires the high K rating, the additional investment may not be justified. Furthermore, the larger size and weight of higher K-rated transformers compose logistical challenges. They require more space for installation and may necessitate structural modifications to support the increased weight. This can add to the overall project cost and complexity. Poor voltage regulation, as mentioned earlier, is a direct result of increased impedance. Voltage regulation is typically expressed as the percentage change in voltage from no load to full load conditions. Higher impedance leads to a larger voltage drop under load, resulting in poor voltage regulation. Sensitive electronic equipment such as computers, servers, and programmable logic controllers or PLC are particularly susceptible to voltage fluctuations. These fluctuations can cause equipment malfunction, data loss, and even permanent damage. Overloading, while seemingly paradoxical, can occur when a high K-rated transformer is not properly loaded. Transformers are designed to operate optimally within a specific loading range. When a transformer is significantly underloaded, it may operate at a lower power factor, which can increase losses and reduce efficiency. In addition, underloading can affect the transformer's ability to dissipate heat effectively, potentially leading to localized hotspots and premature insulation degradation. Selecting the correct K rating requires a thorough understanding of the load characteristics and the harmonic content present in the system. A harmonic analysis should be performed to determine the total harmonic distortion or THD and the individual harmonic components. This information can then be used to calculate the required K factor. It's important to note that the K factor is not the only consideration when selecting a transformer. Other factors such as voltage, current, impedance, and temperature rise must also be taken into account. Consulting with a qualified electrical engineer is recommended to ensure that the appropriate transformer is selected for the specific application. In addition to selecting the correct K rating, it's also important to implement appropriate harmonic mitigation techniques. These techniques can help to reduce the harmonic content in the system, minimizing the stress on the transformer and improving overall power quality. Common harmonic mitigation techniques include using harmonic filters, employing phase cancellation techniques, and specifying equipment with low harmonic distortion. Harmonic filters are designed to block or reduce the flow of harmonic currents. They typically consist of tuned circuits that are designed to resonate at specific harmonic frequencies. Phase cancellation techniques involve connecting loads in a way that cancels out harmonic currents. For example, using a delta Y transformer connection can help to reduce the flow of third harmonic currents. Specifying equipment with low harmonic distortion is another effective way to minimize harmonic problems. Many modern electronic devices are designed with built-in harmonic filtering or power factor correction circuitry. These devices generate significantly less harmonic distortion than older equipment. By implementing these harmonic mitigation techniques and selecting the appropriate K-rated transformer, it is possible to ensure reliable and efficient operation of electrical equipment and systems. In summary, while K-rated transformers are essential for handling harmonic currents, it is crucial to select the correct K-rating for the specific application. Oversizing the K-rating can lead to increased impedance, reduced efficiency, increased cost, overloading, poor voltage regulation, and increased size and weight. A thorough harmonic analysis and consultation with a qualified electrical engineer are recommended to ensure that the appropriate transformer is selected. Implementing appropriate harmonic mitigation techniques can further enhance power quality and system reliability. Consider a scenario where a commercial building has a significant amount of LED lighting and variable frequency drives powering the HVAC system. These types of loads are known to produce harmonic currents. If the building's electrical system uses a standard transformer that is not K-rated, the transformer could overheat and fail prematurely due to the harmonic currents. To address this issue, an electrical engineer might recommend replacing the standard transformer with a K-rated transformer. The engineer would perform a harmonic analysis to determine the appropriate K-rating for the transformer. If the analysis shows that the system requires a K-9 rated transformer, installing a K-13 or K-20 rated transformer might seem like a conservative approach. However, as discussed earlier, this could lead to several problems. The higher K-rated transformer would have a higher impedance, which could cause voltage sags and disrupt sensitive equipment. It would also be more expensive and less efficient than a K-9 rated transformer. In addition, the higher impedance could limit the available fault current, which could compromise the performance of the overcurrent protection devices. Therefore, it would be more appropriate to install a K-9 rated transformer and implement other harmonic mitigation techniques, such as using harmonic filters or specifying equipment with low harmonic distortion. This approach would provide adequate protection against harmonic currents without the drawbacks of oversizing the K-rating. Another important consideration is the impact of the transformer's impedance on the overall system impedance. The system impedance affects the voltage drop under load and the fault current levels. When adding a transformer to a system, it's important to ensure that the transformer's impedance is compatible with the existing system impedance. If the transformer's impedance is too high, it could cause excessive voltage drop and limit the available fault current. This could compromise the performance of other equipment in the system and increase the risk of electrical faults. Therefore, it's important to perform a system study to determine the appropriate transformer impedance. The system study should take into account the existing system impedance, the load characteristics, and the overcurrent protection requirements. By carefully considering these factors, it's possible to select a transformer with the appropriate impedance and ensure that it integrates seamlessly into the existing system. In addition to selecting the correct K-rating and impedance, it's also important to ensure that the transformer is properly installed and maintained. Transformers should be installed in a well-ventilated area to prevent overheating. They should also be inspected regularly to check for signs of damage or deterioration. Proper maintenance, such as cleaning and tightening connections, can help to extend the life of the transformer and prevent failures. Furthermore, it's important to protect the transformer from overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, should be properly sized and coordinated to protect the transformer from damage. Regular testing of the overcurrent protection devices is also recommended to ensure that they are functioning properly. By following these best practices, it's possible to ensure the reliable and efficient operation of K-rated transformers and minimize the risk of electrical problems. The K factor is determined through a harmonic load flow study, which involves measuring the harmonic currents produced by the nonlinear loads in the system. This study typically requires specialized equipment and expertise. The electrical engineer would use a harmonic analyzer to measure the harmonic currents at various points in the system. The harmonic analyzer would provide data on the magnitude and frequency of the individual harmonic components. This data would then be used to calculate the K factor using a standardized formula. The K-factor formula takes into account the weighting of each harmonic component based on its effect on transformer heating. High-order harmonics have a greater impact on heating than lower-order harmonics. The formula also takes into account the transformer's design characteristics, such as its core material and winding configuration. Once the K-factor is calculated, the electrical engineer can select a transformer with a K rating that meets or exceeds the calculated K-factor. It's important to note that the K-factor is not a fixed value. It can vary depending on the load conditions and the operating characteristics of the nonlinear loads. Therefore, it's recommended to perform the harmonic load flow study under typical operating conditions to obtain an accurate K-factor. In some cases, it may be necessary to perform multiple studies under different load conditions to determine the maximum K-factor. The transformer should then be selected with a K rating that is sufficient to handle the maximum K-factor. This will ensure that the transformer is adequately protected against harmonic currents under all operating conditions.